is actually positioning start from system model or singular model and tell about how to do the positioning measurements, such as music algorithm and the course synchronization, and how to mitigate the multipass. And the most important is the location estimation algorithm. The most popular is maximum likelihood estimation. And particularly, we try to introduce the particle swarm optimization. This is a brute force search algorithm so that we can directly search the location. Lastly, we introduced the performance of the 3GPP evaluations, but I just add one page and show our 5G trial.
Hi, Wang Yi, I think you're muted or something. We cannot hear you.
Can you hear me?
I can hear you.
Can you hear me?
Yes, I can hear you. Yes, I can hear you.
Can you hear? 这个吧 Can you hear me?
Yes, I can hear you.
Yes,
I can hear
yes,
you,
I can hear
but
you.
we can't see your presentation.
Okay. Maybe I don't know. It's because I shared. Can you see me now?
Yes.
Okay. I just shared the screen in our meeting room. Okay, sorry. So let's repeat the contents again. And this part is talking about positioning tactics. Start from the single model, positioning measurements, particularly, and course synchronization and refined synchronization, and also how to deal with the multipass mitigation. And lastly, we introduced the maximum likelihood estimation to estimate the location. But we would introduce the new just the methods, which is called particle swarm optimization. This is a brute force search algorithm and used to find the estimation. Lastly, we introduced the 3GPP evaluations in about all the just the positioning techniques. We also added one new just the results that's about the Taichan factory using our 5G test bed. So that might be very interesting because it's we use the carry phase to reach a high accuracy there. So let's revisit what happened in 3GPP. Actually, we just summarized about eight just the tactics defined in 3GPP. And the first two is evolution positioning. That's I mean just from the LTE, just the positioning techniques like the enhanced cell ID, and uplink and downlink TDOA positioning, and this all are standardized in LTE. In NR, just using NR like the alphas, like the reference singular to do the measurements, and reuse the LTP or NRPPA to the RMF to do the positioning. Some new just techniques are introduced in right hand. First, like the angle-based positioning. Actually, this is much contributed from Huawei. And multi-cell RTT, and this is much contributed from Qualcomm. And release 18 is working on the carry phase positioning, and currently much. Also, we don't yet have final results, but the main contribution are working on the just the phase difference of arrival in uplink and downlink. The first one is multipass assisted positioning. This is not just explicitly read in the standards. It just says multipass can be reported to the location server. But in that case, we can use the reflection pass and so that we can have a base station, they can have a reflection path if this is mirror, and they can have a virtual and to send the signal. In that case, we can improve the accuracy of the positioning, particularly if we want to use only single G B to do the positioning. In that case, we have the loss, use the RTT and AOA, but in NLOS, we can use the reflection path to track the location. Actually, this is quite interesting, just the positioning, and has been studied in past a few years quite forward. Actually, positioning the theory for the positioning is a problem for estimation. So estimation just has been just studied by Kramerov Norban, and this bunch just tell us given a singular to noise ratio and a channel, well, for example, like AWGN channel, and what's the band to reach for the estimation. For example, if we use the TDOA, actually, we first need to get the TOA timer for arrival, right? And in this case, the TOA is bounded by this formula, and we can just say, we should say this bound is variance, something like the residual MMC. So if we say the location TOA error as we need to have a square, root square of this formula. So in that case, we can say the positioning error is linear to the, almost linear to the bandwidth. That means big bandwidth will have much higher, linearly has higher accuracy. But normally we use the CDF of 19% or 75%. In that case, is not so linear, but approach to linear. Another one is depends on the signal to noise ratio, and particularly in the OFDM, this is formulated in this way. And we should note that the SNR is normally is given in the output of the cause synchronization, or the output of the correlation. The second one is angle-based positioning, and actually this depends on the number of antennas. If we given the antenna interval is half of wavelength. So in this case, we can say it also depends on the signal to noise ratio, but we should note that this depends on the number of antennas here, but this is not linear. Not linear. Another one is depends on the distance between the 0B and the UE. Because you can see, given an angle error more far away than the location error will be larger, right? Another one is depends on the angle of arrival, because if the angle is just in direction of legal or both side of the direction, actually the error will be small. But if you go to the edge, that will become larger, the error. Let's see what's happened in the carrier phase. Actually, carrier phase is just mentioned by Shu. Actually, this is significantly better than the other positioning tactics, because it depends on the carrier frequency FC, and and this is always much larger than the bandwidth, right? So give an example, and if we have 3 GHz carrier phase, 10 dB bandwidth up for 100 meters and 16 antennas of AOA, we can calculate like the CRB for tau submeters, and angle also like the DC meters never, and but for carrier phase it can reach the sub centimeters. So this is quite good. So let's see how to formulate the algorithms. This is the single model. Let's start from the very beginning, and given a number for just the 0Bs, and in the uplink, for example, just sending the sounding reference signals and denoted by this, and its location is unknown and should be uniform distributed in a square area, in this area. So the received singular y at the 0 to be n and antenna m will have just the multipass affected the singular and plus with the Gaussian noise, right? So this is the general form of the received singular in multipass environments. So next is introduce the measurements and the location. Actually, in the uplink, the 0B has the received singular, and in the baseband, and firstly do correlation and to find the peaks. That's the coarse synchronization. The third one is has the window field, so that they can field the multipass impacts. The third one is to refine the TOA measurements or AOA measurements. And this is a super resolution algorithm like the music. You can also use some other algorithm like the Esprit or some EM. But from our experience, music has the best performance as well as the robustness, as we know. And lastly, if you find the first pass of arrival, and you can estimate the phase of that pass. And all the measurements will be delivered to the location server. That's called LMF, and that you can calculate the GDOA, PDOA, and use the measurements you can estimate the location. Always we use the maximum likelihood algorithm, but here we try to just introduce the PSO algorithm. So this page, the next 3 pages to introduce the details. So given the received singular, first we to do the correlation as mentioned before. Correlation has the received singular and to do correlated to do in this formula with the non-SR sequence. Normally the sounding defined in 3GPP is that of true sequence. So that of true sequence has uniform distributed in frequency and may occupy the 1, 2, or multiple symbols in time domain. But if you're using in the frequency domain, if we change the ZC from the frequency domain to time domain, actually is also an ZC sequence. So the ZC sequence has perfect autocorrelation and almost perfect cross correlation, just the coefficients. So normally we call it the ZC as the perfect sequence. So next, if we have the correlation spectrum, and then we can select the peak. The peak is we can select the peak means the in sense of amplitude or power, and in that case we can find the delay corresponds to the peak, right? And normally if we have some multipass, actually we can find using some early window to find more just the pass in advance of the peak pass. In that case we can find some weak first pass, but that's some based on some just the practical just the channels, right? So in that case we can find the costly, we can find the delay of the first of arrival. That's the tau in that case. Next is how to reduce the multipass. Actually, if we find the first pass, and if we have any reflection pass just near to the first pass, for example, like the stronger reflection pass or some other pass close to the first pass, it's very bad if the pass has 2 or 3 samples or even one in one samples. That will greatly affect the delay of the first pass. In that case, normally we use a window or a field, no matter it's in time domain or frequency domain. But a simple way from our view, like in 3GPP simulations, we use the time domain window. That's the simplest way is to have a rectangular window applied to here, the WK. So WK. Normally we can the window length normally like from the 10 samples to even like the 3 samples, depends on the channel to apply. Okay, so when applied this window to mitigate the multipass then lastly we use this coefficient and to apply to refine the TOA. This the traditional just the music algorithm. For example, this EK here EK is the steering vector. For example, like the steering vector of the channel, and VI is the noise space of the channel. No matter here we use the CIR that's in the time domain, and in that case, steering vector we can use the K here is something like the delay, and the VI is the topic of the autocorrelation of the EHH, right? So in that case, you can estimate the correlation, just the the channel matrix, and then get the noise vector, and then using the steering vector to search over all the just space to get the spectrum get the spectrum, and then select the largest one that corresponds to the delay. So this is the music. Okay. Lastly, the measurements is to have the TDOA. This is quite simple, right? For TDOA, just to have the TOA measured from the 2 GLODBs and to do minus to subtract to take one of the GLODB as reference and then subtract the TOA from the another TOA measurements. So for phase, just note that the correlation, because we're just using the ZC sequence to the correlation with the received signal, actually that doesn't change the amplitude and the phase of the CIR. So all the information are actually reserved in the correlation spectrum. In that case, we can use the to take the IQ and to calculate the phase of that sample, right? So it's quite simple. Phase is very simple. Sometimes we can use the MIMO, like the maximum MIMO, like in outdoor in the macro base stations, we can have 64 just the RF channels and even more multiple antennas. In that case, we have to combine the phase from the older antennas. In that case, we have to remove the impacts of the angle of arrival to the phase. So in that case means that we'd better to first estimate the AOA and then remove the AOA impacts from the phase estimation, and then combine all the phase from all the antennas. That will be better. Okay. Next is the differential. That means because why we introduce differential PTOA, the problem is normally we have for synchronization is quite a problem. Like for UR-TDOA, we have delay errors between the GLODBs. Even we're doing some synchronization, like the GPS synchronization, we still have tens of nanoseconds synchronization error, right? So the first one is we have to remove such synchronization error. The second one is for phase. Actually, for phase, we have the error of the initial phase. No matter it's in the UE side or GLODB side, we meet such problem. For example, as far as we know, using the existing 5G commercial terminals, actually the initial phase is almost random. So in that case, how to remove such errors? Here in 3GPP, we introduced the reference point. Reference point can be a UE or a GLODB, but the main understanding is the UE. So given a reference UE, if we can send the something to the board GLB, and we can also measure their like the TDOA, PDOA, such measurements. It's noted that the imperfect factors in the UE or in the GLB can be removed if we use the differential PDOA or TDOA in that case, right? This is quite similar to the RTK in the satellite position, because in the RTK, we can, using non-location of the RTK node to measure all the errors, like in the L interface from the satellite. This is quite similar in our 5G. So using this, we can using the differential, just the differential operation. In this case, this is is quite simple from the formula, right? This is a TDOA, PDOA, and the differential TDOA and the differential PDOA. Okay, so here we introduce the reference point here. Okay, given the measurements, the problem is how to do the to estimate the location. The maximum likelihood can be used the maximum likelihood value. That means given the measurements, no matter is POA, TOA, or TDOA, PDOA, or AOA, and given that, and to estimate the UE location X, right? And here, and this can be changed to this formula. This is joined just the PDF, and this is a distribution of the UE location. Actually, this is uniform distributed in a square error, so this is equal to everyone and can be removed just to maximum the likelihood of this joint just probability. And this one, if we further assume that the errors are Gaussian distributed, this is the IID Gaussian distributed, and then we can this is equivalent to minimize this fitness function, right? So this is something like the Euclidean, just the distance to minimize the distance, and weighted by their just variance. And note that this is the measurements and this is the hypothesis. How to calculate the hypothesis? Hypothesis is, for example, like the differential TDOA. This given the X, you can calculate the distance to each GLB, and also calculate the UE to the first GLB. This is as the reference GLB. So in that case, this is TDOA, and this is also calculate TDOA for the reference point XR, and then do the differential for the two. So in that case, and to minimize the physics function of this formula. Next, if we want to do carry phase, actually we use two steps. First is to using the DTDOA to get a course just the runs, and then use the carry phase to refine the location. In this case, it's quite similar to the time delay. In that case, you can say also, but given the hypothesis X and the D PDOA is a little bit difference, but again, it's quite simple. Just according to the location of GLBs and the reference UE location, and then you can calculate everything, and then you can change this to degree. So given the fitness function, actually maximum likelihood, no matter is DPDOA or DTDOA, actually is something like to minimize the fitness function in this form. So actually in previous, we have developed many just algorithms to approach the maximum likelihood estimation, like the Chang algorithm, Fang algorithm in the 1990 or even earlier. So it's basically something just the approach to the maximum likelihood or something like the least square. We will see that later. But here we just again just reveal some models. Here we model like the distance. Here this is Gaussian distributed. TDA we should have more noise because they have has combined the two sources of noise from the two zeroed base, right? And the error of the angle AOA normally is not so uniform, but normally we have also used the Gaussian distributed or truncated Gaussian distributed function to approach the noise. And this one is just describe some errors in the practical system, like the calibration error in the zeroed B or in the UE side. We have the propagation delay, we have the clock offset, and some such errors. And also we have discussed like the calibration of angle of arrival and calculate the error of the RX, TX time difference. Everything has been discussed in 3GPP. But for simply purpose, we just assume that the error distribution are Gaussian. Maybe it's not so close to practice as far as I know, but it's easy to understand what the positioning work. So this one again, just to minimize us in this way, right? In this way, and so we have the how to estimate the location given the measurements and hypothesis, and there just variance. So actually, this is a nonlinear least square, just a problem. Least square, first the least square, if we have x, y, two-dimensional, actually we have, if we have a 3 base station and using TDOA, then we can have the two equations. In that case, we directly calculate the x and y, right? So in that case, no more just the observation, exactly the same number of equations as the location x, y. And Watson's least square and may introduce some more just the base station to calculate the location. But that's as far as I know, most just no matter in 3GPP, members in 3GPP use is the Chang algorithm, and this one is a two-step least square and can approach the maximum likelihood. And in that case, they can introduce this an intermediate just vector, that's R1, that's the UE to base station 1 distance as a value to calculate the locations. Is some just two steps to calculate that. It's quite interesting one, but it's verified that can be approached to the maximum likelihood estimation. And next is a fun algorithm, maybe earlier. I remember that's in the 1970s developed, but in my understanding, that's a special use case of the Chang algorithm. That's the number of zeroed bits are equal to 3. Actually, there are many just the papers to compare the old algorithm. Still mentioned the Chang algorithm is quite popular, used in no matter in 3GPP and some products. So next, we try to use the brute force to search. This is an alternative method to solve the positioning problem. Actually, PSO is an algorithm of genetic, just algorithm, GA algorithm that's developed in the 1980s in that way, and originally is used for neural network to solve some complex optimization problem. And someone found in 1995, and Kennedy just developed PSO. That's something like to say next some swarm, like a group of swarm, and they can such creatures can automatically find their just the destination, even the destination maybe is thousands of miles away. So they can everyone is strange how they can find their desired location. Actually, basically they abstract the group model as each particle, like the swarm, they can fly, and according to his history road, that's has the best individual just location. Another one is should close to the group best center. So, for example, group center is here, they should close to that so that they can everyone is in the group. So here is the best way is that it has a very simple just equation. The first one is updated with the location, just the plus, and the second one is velocity. Velocity has some random just value introduced here. It's depends on the its previous location as well as its best remembered swarm positioning. That's the group positioning, individual best positioning, so that they can take a better close with each other. And then how to calculate, the key issue is to calculate this one. So this is the fidelity functions, depends on what you want, like TOV in this way. If you have multi-user, just in this formula, they have the 2 U's, they can have the U to U, just the distance, as well as the U distance, right? TOV and the U to U, just distance. It's quite easy to formulate the fidelity function, no matter it's TTOV, AOV, or even some other just the positioning techniques. So next, have a limited just a time slot, and next is some evaluations from the 3GPP. I think everyone can see TR and 38 and A55857, right? 2 documents. We have collected all the just the evaluations from 3GPP, and this has posted some like the TOV, TDOV, AOV, and such measurements, and including the FR1, that's for the sub 6 GHz and above 6 GHz, and this is about the 2 GHz or 4 GHz, and this is 30 GHz. So just mentioned like the bandwidth, number of antennas, and the synchronization errors can all affect the positioning accuracy. But in generally, we even using like FR1 with the 100 megahertz, we can reach about the 0.5 meters at 90%. But that's in very just indoor DH scenarios. For some scenarios, the accuracy can be reached like the 0.2 meters. So this is general just the results. Everyone can check the 3GPP. Lastly, I'm using just 2 minutes to introduce our latest results. That's using our 5G test bed with the Lampside, our product. And this we have research just site in the Taichung, and this is the factory scenarios. We have some areas with some facilities, so that may cause some multipass, but it's not so full, the facilities. And we have eight just the PRU. You can see it takes that as the 0 to B in the cell, and we take put the UE in this side FF, so they can see like the normally they can see 6 0 to B's in the factory, and they send the sounding simultaneous That means the desired UE and target UE and the reference UE has sent the sounding simultaneously in one or of them symbol, but they divide differentiated distinguished by the this code. Okay, so but normally it's orthogonal with each other with the carry frequency of 4.9 GHz and some parameter scale. Okay, this we just verified the 3 positioning techniques. One using the ULTDOA, but here ULTDOA has almost perfect synchronization, because in advanced we measured many points, and so that we can calibrate the synchronization error before. So this can achieve the next 0.2 or 2.34 just in this range, and to have this range. And this one is a differential TDOA positioning accuracy is a little bit worse than the perfect TDOA. That's understandable because still we have synchronization error scale. The best performance is the DPDOA. Here we has measured 4 points, and each point we have collect 500 just measurements there. So or just the 4 size and collect the, and then we can have the 67%. We can reach the centimeter. This is really centimeter, never just the accuracy, you can see. But still in the 90% is hard to reach centimeters level because of like the multipass effects, like some imperfect factors. So still we are working to improve the performance. Maybe in the future we will can present some more wonderful just results here. Okay. So that's my presentation, a little bit late. Maybe here, the last page is some job opportunities. If everyone are interested in our wellness research department, you can just remember the context here. And we have locations in Beijing, Shanghai, and many places, Chengdu, and many places. So, but detailed information, you can just find the Chen Zhongping to get more detailed information there. Okay. Okay, that's my part. Dongyan, are you there? Okay, so maybe this, I think maybe is a little bit late, but we will have a break about 10 minutes. Let's come back at 10:35, and then we will start the third part. Okay.
Professor,
okay.
It's break time.
Yeah.
Okay.
We should have a break for 2 minutes.
Yeah, 10 minutes. Come back at 10:35.
Okay.